Thank you very much for the nice introduction. I'm Abhishek. Um, as you've already heard in the introduction, I'm working as a data scientist at a company called Boost.ai. It's a small company based in Norway. So I kind of like the weather here. Even if it's rainy, it's warm. So let's start with the presentation. So I'm going to talk about chatbots. It's revisited because most people talk about chatbots. They talk about neural networks, deep learning models, and don't they don't really tell you how to build one. So we hopefully you will be able to build a chatbot after this presentation. I will show you how and what are the tools required. So uh, here it is the agenda. So I will start with something pretty boring. What are chatbots? So everybody knows what chatbots are. Um, and what are the different types of chatbots. Then we can talk about how these chatbots work, and then we see the building blocks of chatbot, and then trying to create a chatbot. So chatbots were introduced to the world as chatterbots. Uh, that's what Wikipedia told me. So they're usually a set of rules or artificial intelligence. Mostly the chatbots that you see in the wild are a set of rules. So very less of them are doing some real AI. We'll talk about both of them. So they simulate human behavior. More advanced chatbots, they use heavy natural language processing, natural language understanding, and deep learning to accomplish the task like a human being. So uh, they are virtual assistants. The chatbots don't need to answer all kinds of stupid questions that people ask them. They can say no, I don't know about this, sorry. Um, yeah, like some examples are like if you're using some mobile operator like Vodafone, you go to their website, click on the live chat, and then a bot appears. So when most of the times when it's a person talking to you, you won't get the right answer. But if it's a bot, you might get the right answer. Sometimes you're like, oh, sorry, oh, you're talking in German. Can you speak in English? Then the guy goes offline. So that doesn't happen with chatbot. Um, yeah, also in banking industries, it has been, nowadays it's being used quite a lot. So let's see. So like some examples of chatbot are Alice, Eliza. Have you guys heard of these chatbots? Oh, cool. So yeah, Google Home, Amazon Alexa. So like going from Amazon Echo to some of the chatbots that my company has developed, which are being used. And then there are different types of chatbots. So I just put this picture because it looks good. It has nothing to do with this slide. So there are some AI/ML based chatbots or rule based. AI/ML is artificial intelligence markup language. So like HTML, but for AI, as they say. Um, then we have other two sequence to sequence based, and then we have some intent based. So I think most of you have heard about sequence to sequence based chatbots, right? So like training on movie corpus, and then you type something, it responds according to that corpus. So we're going to take a look at that, and also intent based, because in the industries, we don't use sequence to sequence, and let's see why. So we start with the pattern or rule base. So this is what AI/ML looks like. And you have a pattern here, it says hello. So the template is, okay, well, hello, what are you? So I'm a bot, stupid. And similarly, you can have some kind of pattern matching using an asterisk or something. So if a person starts talking some bullshit, then you can choose a random reply from this list. Okay, yeah, blah, 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 yeah, go on. And some people like those kind of chatbots. Keeps you busy. saves the money for a shrink. Yeah, but like, it's the era of deep learning, and companies are using this buzzword, deep learning, to sell their products even if nothing is deep in their software. So they don't learn from it, but yeah. So we focus on deep learning, or we will try to focus on deep learning, but chatbots are not all about deep learning. There is a deep learning component, and there are several others which are very important. So before diving into these, let's see word embeddings. You guys know TSNE? Can you tell me what's represented here? Exactly. Cool. Also, this slide has nothing to do with the image. It just looks good. So we have word2vec. We also have Glove embeddings and fast text. So most of the people nowadays are using Glove or fast text vectors. So Glove is only on English, and then fast text offers you a lot of different languages. So word2vec is pretty old, and Glove is count-based model, which does dimensionality reduction on co-occurrence matrix counts. So if you have a word context matrix, it generates a vector for, it factorizes a word context matrix into a word vector for, a vector for each word. So given the same idea, we can see how word embeddings work. So it's an n-dimensional space, and if I have a vector for, I think it's a very old example with king, queen, and a vector for Berlin. Then we have a vector for Paris and France. And I just take the negation vector of Germany, and then I add France to it. And what I get is something very close to Paris. And in chatbots, how you can use it. So we go to the same space again, and let's say user has a query and he wants to know how's the weather going to be here. And you have few different options. One is your weather service, one is things to do, and something else. So you choose the one which is closest to your query, the reply. And how do you do that? You can do it using some distance functions. So word2vec, Glow, fasttext, they give you a vector for each word, and then you can convert it to a sentence-based vector using something like this. So you take the words, and the word tokenize function that I have here is from NLTK. I'm trying to filter out the stop words first, and then only the alphanumeric. I'm taking only the alphanumeric words. And in the end, I'm doing some kind of, I'm doing normalization based on the counts, number of times they appear. So this gives you a vector for the sentence, and actually works quite good, even in Kaggle competitions, or like general feature engineering stuff. But RNNs. We should talk about RNNs. This diagram, I think it's pretty easy to understand. So RNNs work on sequential information, and the output is dependent on previous input. So my slides don't have any maths, so I don't, this diagram is actually connected to the slide. So I'm not going to explain it, but I'm going to explain it in a different way. So let's say we all go to work, and we have 3 different states. So like you go to the office, or you're working from home, or you just call in sick. So 3 different states. So you decide, let's make a decision based on if it's sunny, I'm going to work from home or call in sick. If it's rainy, then go to office. A simple decision. But that's not how I work. I have a different pattern. And my boss is smart. After observing me for some days or weeks, he found a pattern. That's my smart boss. And first he thought, okay, sunny or rainy, but that's not correct. So I go to office, I get tired, I take a leave, work from home. So I have some free time to kill in the evening. I go out drinking with my friends. And next day, of course, I call in sick. So that's my pattern. Let's represent all these three states with a vector. So let's call this RN the brain. So when we're talking about RNNs, they're like simple neural networks. I have a state of going to the office, which was last seen. And then it becomes my first input in the RNN. The next state is working from home. And just like this pattern, I have, again, working from home and then calling in sick. And again, a repetition. So to understand this better, let's say we have a matrix. That's the RNN. We go to office, the vector, and the matrix. And we multiply it by that matrix, and we get a vector, which is the vector for working from home. So that's basically how the RNNs are working. You're working from home, multiply it by the same matrix, get call in sick. And similarly for the last one. Yeah, this pattern was found out. I was not fired. Yeah, so basically the input goes to the output and becomes the input again, and that's how the RNNs are working. And when we are talking about sequence to sequence, I think this is one of the very famous diagrams by Karpathy. When we are talking about chatbots, you're looking for something like many to many because you have many words coming in and you have different words in the response. So a sequence to sequence model looks something like this here, where H and G are the hidden states. The model consists of two parts. One is encoder and another one is decoder. And the decoder part is for the predicted or target sentence. Each hidden state is a function of previous hidden state and the embedding of the word in that state. This is one of the ways sequence to sequence will learn, but is it the optimal way? No. So then what we do is we just add the previous words to it. So in this way, the model performs much better. But how to make predictions using this kind of model? So one of the ways is a greedy method. So you have an input sentence, hi, how are you? It goes to the encoder decoder, produces three different outputs, the top three predictions, and you choose the first one. Then you add it to the original sentence and continue. And this process goes on for a long time till you stop it or till you encounter a kind of N token if you're using one. And in the end, you have the response for the question. Another one is beam search. So you produce all kinds of outputs possible, and then you select the best one based on the probabilities. So here I'm selecting I am fine, okay. But why doesn't it work? Because it takes a lot of time, a lot of data, a lot of training, a lot of LSTMs. So first problem is not all responses are good enough. And it can only give responses like it has previously seen. It's not very specific. But we are not here to talk about sequence to sequence. Because if it doesn't work, leave it alone. If we are talking about the industries, we don't use sequence, we use intent-based chatbots in the industries. So in intent-based chatbot, every chat has an intent associated with it. RNNs are used with and without sequence to sequence. It is basically a classification problem, but it's not easy as it sounds. Because when we are talking about text chats, then there's a lot of pre-processing going on. So there are 4 different steps. One is the user input. Then most of the time goes in pre-processing of the data. Then you build a model which classifies your questions to the intents, and then you produce a response based on a selected list of responses that you have. So let's look at pre-processing. It consists of many different parts. I'm going to explain 7 or 8 of them here. First one is language detection, then cleaning up, tokenization, stemming, some synonyms or stop words, spelling correction, compound splitting, and entity recognition. We'll come to that one by one. So if somebody writes like this, what's the price of losing my OD? I don't know. So we need to process it somehow and generate a text which is understandable. You can also use character-based models, but they won't work properly. Yes, if you're building a chatbot which is multilingual, of course the first step is language detection, and it's a very crucial step. So you can use some pre-trained models like LangID or FastX, trained on so many languages, or you can build your own model. So for LangID, this is how you can use it. You can invoke it, and then it runs on your local host, and you write this as a test, and you get a response with the language and the confidence. So you can use LangID if you want, but you can also build your own. So you have, let's say you have 4 different languages. You grab the Wikipedia data, you divide them, tokenize into different sentences, and then you can use a very basic TF-IDF model with a logistic regression on top of it. And that's going to perform very well. So this is the TF-IDF I use everywhere in all Kaggle competitions without any change of parameters. I've removed stop words because we're dealing with different languages now. And it works. Or you can build your own deep learning model using Keras. Be cool. So here I'm using one-dimensional convolution and GRU layers. So first of all, you collect the data. Here you can see like I store the data in a text list, and corresponding to every entry that I have in the text, I have a label, which is the language. So I use a Keras tokenizer here, set the maximum length to 300 words. Depending on how powerful GPUs you have, you can do more. You can also create a generator, but I'm loading everything in memory at the moment. Then all the sequences are all the texts are converted to sequences, which are basically vectors. And if you have less than 300 words in a sentence, then we pad it. So we use the pad sequences method here. And in the end, we get a word index. Word index is nothing but a dictionary, which has all the words in the corpus. And for every word, you have an index. The next step is the model itself. So I started with one embedding layer, a GRU, and then a convolutional layer. And what I do is like I concatenate the output of the convolutional at GRU layer, and then I just throw in a batch normalization and a dense layer. You can avoid that if you want, but make sure you use dropout, otherwise you might be overfitting. You can also use spatial dropout after the embedding layer. And then I have to compile the model for the number of languages I have, which in this case was 4. So we built a language detection model at least. Now it's a cleanup task. People write bullshit when they're chatting, so they use a lot of abbreviations, unnecessary or unintentional characters, emojis, symbols. these kind of things. So we need to clean up the data before building these kind of models. And to do that, you can use something as simple as this one. If it is alphanumeric, keep it, else eliminate. Or you can replace the characters specifically. So for some tasks, if you want to build an entity recognition for email, let's say, you might want to keep @ symbol or percentages in again in an entity recognition, but I don't think they are required for language detection or classification tasks. Or you can use regex based. Then we go to tokenization, which is again very important step. I mean, all the steps are important. I've been writing that on all slides. And it's not always about spaces. Like most people think, it's okay, tokenization, okay, I split by spaces. But what will you do if you are dealing with Chinese language? So you have to convert the words into different tokens, and it might be different for different languages. So the simplest way is to use the word tokenizer from NLTK, since we are not dealing with with Chinese language at the moment. So we can just use word tokenizer, or you just write your own. And this is how you can do it, like few lines of code. So you have to download this Punk package from NLTK, and then if you print this, you see like it's also separating the comma and the question mark and everything. So you get a list of different tokens in the sentence. Then we come to stemming, which is reduction of words to the root form. And why is it important? Because we'll see. So like somebody is talking about phishing, and it can write different forms of phishing, which is basically going to the same thing, fish. So for these kind of tasks, why do you want to keep so many words in your neural net? Why do you want it to learn so much? So you can use this stemmer. So I prefer using snowball stemmer, or just find one if it's a language which is not available in NLTK. And if it's not anywhere, then learn the language or ask some linguist to do it for you. Now, with stemming, we can also use lemmatization. We don't use it usually because it's difficult for every language, and you don't find them freely available. Snowball stemmer you can find for many languages, not all. Then we come to synonyms and stop words. So this is a Norwegian word for sikring. I don't know if I'm pronouncing it well. Means something. Or a German word for the same thing. I'm not pronouncing any of them. Spanish, Lithuanian, and Polish. And now you know all these words mean the same thing, insurance. And when you're dealing with different languages, you want to keep your data. You want to build a single model for different languages. You don't want to build a model for French. You don't want to build a model for English. So it's better to convert everything to one base language. And that's why we use synonyms in chatbots. Similarly with stop words, many people would like to remove stop words, but what if you are interested in the structure of the sentence? So if somebody is asking, I need a car insurance, can you tell me about it? So the topic is car insurance, but then you have words like new, need, or myself is I, which are stop words. So you will remove them, but then you are losing a lot of information. So we build a list of, for chatbots, we should always build a list of stop words on our own, which we think are stop words and won't matter even if they're removed. Next, we can go to spelling correction, which is also a very crucial step. So if somebody is writing like this in the chat, can you tell me about news in Kotlin, whatever. Of course, your model will fail if you don't have a proper spelling correction. So what you can do is use Peter Norvik's spelling correction, which is quite famous, but let's try building our own. And to build so what I'm doing is I'm taking a sentence and I'm introducing some impurities in that sentence. So all these sentences are the same except for the fact that there are many impurities. And then I send it to a bidirectional character-based LSTM model, which learns on the original sentence. And you have to, it takes a lot of time to learn, but it performs very well. So how I introduced impurities using Peter Norvik's edits. So you have edits 1, which is deletions and transposes, replacements of words, or inserting a new character. So you have a list of characters, and when you're dealing with different languages, you can also include other special characters if you want. You should. And then edits 2 is just a function which is the second edit in the word. So you can use these functions and introduce impurities in the sentences, train a character-based LSTM, and you should be able to build your own spelling corrector. The next one is compound splitting. So compound splitting is, this word means car insurance, but it's made from 2 different words, which is car and insurance. And we have similar things like Kühlschrank is refrigerator, and it's also 2 different words. So they can be 2 words or 3 words, or some person might also write like this, and you need to split it into different words. Kind of a tokenization, let's say. Unfortunately, I cannot talk about compound splitting in details in my talk, so we can take it offline. But the next thing is entity recognition, which can also be achieved in several different ways. And it's important because in one of the examples I showed, the person was asking about insurance for his Audi. So even if we know like he's asking for insurance of a car, and then we understand what brand of car, then it's more interesting. And you can use some basic regex-based matching for this. So, or build a deep learning-based entity recognition. So let's see if for this sentence, I want to book my flights from Stavanger to here. And you have 2 different cities. So how would you extract these cities? Maybe use a word list, or you can, for these kind of simple things, you can just do a pattern matching. So you just extract to and from. And you have both the cities, then you can send it to a list of cities, word list, and you can check if these are cities. What you can also do is, like let's say you have 3 different sentences, and you want to build an entity recognition model. So when you build entity recognition model to identify cities or locations, so you make the features as 0, 0, 0, 0, 0, and 1. And similarly for the next one and this one, wherever you have the city, and then train a neural net. usually a bidirectional RNN, and of course with a sigmoid in the end, because you can have multiple cities, let's say. And then it will give you output like this, so it should be able to identify cities. But it takes a lot of time to train these kind of models, and also a lot of data. So when you have very less amount of data, what you can do is just use a pre-trained word embedding model and fine-tune it. And why fine-tune? Because it's faster, and it's not always better, but most of the times it is better. And why should we reinvent the wheel? So I'm showing example of why fine-tune. Sometimes fine-tune performs very good, sometimes it doesn't. So let's say I have a two-class problem, and I initialize with random weights. I get something like this. And this is the pre-trained, just using the pre-trained model as it is. But when I fine-tune it, I get something like this. And I didn't make up this data. This is from one of the competitions. Unfortunately, not Kaggle. So you have the fast text embeddings, and then you can retrain using bag of words or scriptgram, because it offers these two. You keep fine-tuning it, and then you have the vectors for the cities. So yeah, I mean, in the end, like, we're moving again to the original task. So we have reached from here to here now. Now we want to build a model for classifying, but how to make data for it? So the data is something like this. It's a hierarchical classification task. So you have insurance, then you have car inside the insurance, then let's say price, mileage, new, whatever, and then you have several other intents like this. Insurance for health or funds. So you try to build a model which is hierarchical. You can do it in several ways. But for that, we first need to create some training data or get it from somewhere. So people usually prefer creating their own training data, because working for a specific industry, you should have specific data, not very general data. So here I make 5 different training messages. And these training messages belong to these classes. So if a person is asking about price of car insurance, then I go to insurance, then car, and then price. Or investments. Okay, so in the end, you have to build a neural net. You can do it in several ways. And when you have built this kind of classification model, let's say everything, it's not hierarchical, it's just simple classification task. So you build a simple neural net model with embedding layers and the RNNs, whatever you want to use. And once it has started predicting well, then you can do some same kind of hierarchical predictions on it. So in the end, you get insurance, car, and price. So that was about the intents. So what the user is thinking, what the user is talking about. And now we talk about sentiments and try to see if sentiment is also important. So people write a lot of stuff to the chatbots. Sometimes they are also very vulgar. But like these kind of things, and you want to know what is the sentiment so that you can improve your bot further. Like in this sentence, if you're using a simple machine learning model, or just, let's say, just rule, and you say, oh fuck, then he's talking crap. But you can build more advanced sentiment models using attention. So here I'm showing the model from DeepMoji. And it looks something like this. You have the text, then 2 bidirectional LSTMs, and then an attention network. So it's an attention network, and then you have the softmax at the end to predict the emojis. So how they show it on their website is something like this. You write, "You are so nice," then it shows here how much weight has been given to every word, and then of course the emoji. So they used a lot of data. But these weights here are not attention weights. These weights are derived like, you have a sentence like this, you find out, okay, this is going to this happy face class, and then you remove a word, and then see how it changes the probability distribution. So you keep on doing it for every word, and in the end, you get the weights for remaining words. You can average them. So attention model doesn't perform the same way as humans, at least in text. Okay, so that was about chatbots. Now we can try to build one. So I thought it would be cool to build a reverse chatbot, like what Google did a few days ago in Google I/O. So it was reserving table in a restaurant. So I wanted to make a bot which can order pickup from a restaurant. So then again, we come to the data. How should the data look like? What models can we use? And what kind of bot? Call it order bot. So I just created some data on my own. Takes 10 minutes. I created different intents like welcome, name, and order. So if the person is saying, hello, how are you, okay, then it goes to the welcome intent or similar. Or what's your name? Can I have your name, please? And what would you like to order? What would you like to eat? And similarly, 2, 3 more intents. So now we are not going hierarchical because it would be a bit difficult for me to explain right now. So just single classes, 6 different classes. And what you want. So like your name, your phone number, you can put your address in. What would you like to order? So basically when we are ordering from a place where we cannot pronounce the names of the things we have in the menu, we just say the number. I'll have 104, 107, and whatever. And what kind. So you like it delivered or pick up. And you can do it easily using, so I'm using some very basic models here. And you can easily do it using scikit-learn. So what I'm trying to do is I have the restaurant intents and the bot intents. I create the data. The data here is a text available from all the classes that we have created. And you open the classes to the list of classes, of course. I put everything in a data frame then, and here I'm just randomizing the data. Then I use a simple TF-IDF, transform it, and a logistic regression. So you can ignore C equal to 100 because it depends on your data. Yeah, you can see like here I'm also using text-to-speech client, which was from Google Cloud. But unfortunately, I have not included it here after this. So I say, okay, I have these set of rules. If prediction is welcome, okay, say these kind of, say like I would like to make an order for pickup. Or you can just use a list of different sentences and randomize them. And this is basically the last final prediction. So you get the string. So if you build it in like a phone call API or something like that, you can use speech to text, convert it to text. It gets the it gets transformed from TF-IDF that you have already done. You get the predictions, and then you can fetch the response from the fetch response function from previous slide. Yeah, I think that's basically it. And thank you for listening.